So I'm going to talk a little bit today about the Jones Center and about what our interest is in geographically isolated wetlands and kind of how we got into this project, and then Francis is going to follow up for there about the project specifics. This is one of our isolated wetlands. It's not very wet. We're actually going through a pretty historic dry period right now. It doesn't seem like it's going to get any better anytime soon with the El Nino and the strength of the El Nino that's out there in the Pacific forming now. But normally you'd see 1 meter to 1.5 meters of water above that ground level in there. And that, I'll just point out another thing, in the background, what you think is fog, that's actually smoke from prescribed fire that's going on near the wetland and actually followed up going into the wetland. We do a lot of prescribed fire at the Jones Center. So what is the Jones Center? We are a private nonprofit. We do research, education, and conservation. I'll talk a little bit about that mission. We've been around for a while, since 1991. I've been there since 2014. The site itself is called Itcheway, or Itcheway Plantation. So the Jones Center and Itcheway is our full name, but Itcheway Plantation is 30,000 acres. We have about 85 full-time employees. About a third of those are in research, and then the lion's share are in conservation. Plus we have on site at any given time anywhere between 20 and 40 graduate students. So it's a pretty active community in the middle of a very rural community, which is Baker County, Georgia. Much of our research and education does center around graduate students, so we co-advise graduate students like Sir and Jana here. We've actually had over 190 graduate students to date graduate since the early 2000s when we started that program. I have to talk a little bit about the history, how we got to where we are. We were the hunting plantation in the southwest of Georgia for Mr. Robert Woodruff in the upper left-hand corner. He was the chairman and CEO of Coca-Cola for about 50 years and took Coca-Cola from a small regional operation in Atlanta up to a global powerhouse. The Jones Center itself is actually named after his personal secretary, which is just to the right of the gentleman next to the Coca-Cola sign. Joseph W. Jones was sort of his right-hand man for a long time, and after Mr. Woodruff passed away and the land got inherited by his foundation, they decided to name the research center after Mr. Jones. We still carry forth a lot of the traditions that sort of helped establish the Jones Center. One of those is quail hunting. It's probably too long of a story to go into today, but the longleaf pine ecosystem would not be around today if it weren't for a lot of landowners in South Georgia, Southern Alabama, North Florida that wanted to manage the land for quail hunting. The ecosystem used to be 90 million acres. It's probably about 4 million acres now. Those 4 million acres were mainly preserved either through military installations or through quail hunting plantations. Here's the shape of Jones Center here on the right. There's the location on the upper left. The shape is a little odd because Mr. Woodruff, again, assembled these lands in the 1920s through the 1940s from a lot of private holdings, and he also wanted to avoid too much highway frontage, so some of the gaps in there are just from not purchasing land along highways. The sort of medium green is all of our longleaf pine, which makes up almost 20,000 acres of the 30,000 acre property. And then we also have about 100 to 120 isolated wetlands on the property. And that's what you see in the lower left-hand corner. This is what we call a marsh. And I'll talk a little bit about our classification in a minute. Our mission, this is sort of the corporate speak for a minute, but is to understand, demonstrate, promote excellence in natural resource management. So really what we do is we serve as sort of an outdoor laboratory. My lab does a lot of the field work that people like John and Sir and Jana rely on to validate remote sensing products, for instance, or to validate models. And so my lab is out in the field almost every day, collecting data from data loggers, or making measurements on trees, or walking shorelines of wetlands. So they do a lot of the grunt work on the ground, a lot of the hot grunt work. Our research program covers 3 kind of broad areas. Our director loves alliteration, so he came up with this woods, water, and wildlife. But everything that we do kind of falls in that scope. There's only 9 scientists there, but we're pretty broad in what we do. The wetland program kind of falls in between that woods and water section, although we also work with the wildlife biologists quite often on that. Why are we interested in wetlands? The Jones Center, again, that's highlighted in yellow, is this in the center of a region with a gray outline and all the little gray specks called the Daugherty Plain. The Daugherty Plain is a physiological province in southwest Georgia that goes into North Florida and Alabama. And I think Francis is going to talk a little bit about this more lately, but it's a karst region. So it's a lot of limestone bedrock, a lot of sinkholes, a few caves, so well-developed caves. But it has over 11,000 of these small depressional wetlands in it. Some of those wetlands look fantastic, like the one that's on the Jones Center in the upper right. That's a forested wetland that's very pristine, never disturbed. And then some of them, like this wetland on our boundary next to an ag field, that are highly disturbed. And so this adds to our ability to compare wetland management and to sort of learn everything we can about the human impacts on wetlands. So why wetlands? Again, we as a center focus a lot on applied research, and so a lot of what we do is ecosystem science, but it's bent towards some kind of human application. And so a lot of what we do is on wetlands is centered around the concept of ecosystem services. If you've never heard of this, ecosystem services are basically benefits that humans get from natural ecosystems just through the function of the ecosystem. So there's not necessarily a heavy management component. It's just the ecosystem exists. It filters water, it provides fiber, it helps soil form, it regulates climate, all those things that we rely on to have a stable ecosystem. And wetlands are a big part of that. Wetlands also are a part of this idea of nature-based solutions. And if you haven't heard of that, I'll give you sort of the basic definition is a responsive use of ecosystem services as tools to mitigate human impacts on the environment. So if you wanted to mitigate water pollution, you might build a wetland to have the water filter through the wetland. Or if you wanted to mitigate climate change by sequestering carbon, you may create a wetland or manage a wetland so that it was collecting a lot of carbon. So the application of ecosystem service concepts to real world problems, that's a nature-based solution. Just wanted to say a quick word about biodiversity, because I'm going to talk about biodiversity in the next slide. Biodiversity is not necessarily an ecosystem service or a nature-based solution, but it underpins a lot of what we value in ecosystems, because it can provide, aside from the moral implications of preserving biodiversity, biodiversity can underpin sort of a functional redundancy in ecosystems. So if one species disappears or has a couple of bad years, then another species can kind of pick up the slack for productivity or some other function. And one of the things we know about wetlands is that wetlands are often hotspots for ecosystem services. So this is just, again, a biodiversity example, but this is from a paper published a few years ago about endemic species and the number of endemic species in the United States. And you can see that there's a lot of correlation in the southeastern United States, especially in the southeastern coastal plain where we work, between the location of wetlands and the location of endemic species. So whether it be plant species or amphibian species or some other bird species, wetlands tend to concentrate ecosystem services in small areas. And even highly impacted wetlands can provide very important ecosystem services. So this is a wetland that Sir and John has worked on quite a bit. There's actually her and Francis in that middle of that pond there. And they're collecting sediment cores and measuring how much sedimentation gets trapped in these wetlands so that it doesn't go downstream into local rivers. We're in the Flint River Basin, and that's an ecosystem that we do a lot to protect. And these wetlands, even in this ag field, provide important services in terms of nutrient capture and sediment capture, but also wildlife habitat and climate regulation. So wetland research at the Jones Center is intrinsic to what we do. It's part, again, of the Woods and Water programs. We've been studying the hydrology of these wetlands for a long time using staff gauges. So what that means is that gauge on the left-hand side is just sitting there in the wetland, and we have a technician that goes out and manually reads it every 2 weeks, and he's been doing that for 30 years. More recently, and he's done that at 42 different sites, so I know the map's a little confusing, but all those dark green dots are wetlands that we have staff gauges in. We have other programs. Again, you never know where you're going to see it at the Jones Center. There's a student there in one of the student work areas, and she's carrying an alligator. So your eyes are not deceiving you. That's an alligator in the office. More recently, in 2017, we installed hobos to measure water level in a subset of these wetlands. So now we have a data set that is every 15 minutes of wetland water level for 18 of those wetlands since 2017. Just to put things in a little bit of perspective, I love this quote from a USGS scientist. I can't remember his name, but he said long-term data is the antidote to short-term memory. And we're starting to really reap the benefits of some of this long-term data now. For those of you who may not be as old, we've been collecting data since the biggest movies were Forrest Gump and The Lion King. And the biggest news story that year was O.J. Simpson. And the Dallas Cowboys were actually a good football team back then. So it's been a long, long time since we've been collecting these wetland data. Again, we have different types of wetlands. We classify them basically according to vegetation types. Marshes are your no woody species. Cypress savanna is sort of a low basal area forest down there in the bottom left. And then the cypress gum swamp, which is extremely dense forest, closed canopy. And we have kind of an even distribution of these three across the site. And then more recently, in working with Francis, we've done a lot more work on these geographically isolated wetlands that are embedded in ag fields. So you'll see a little bit of that today. One of the central concepts of why we measure hydrology the way we do is that hydrology is a master variable in wetlands, just like flow is a master variable in streams. It controls hydro period, which is just the length of inundation. It has effects on carbon and nitrogen cycling that we're still trying to understand. And then it also affects connectivity of wetlands. So just looking at these two bottom images, this is actually an image of a place called Richardson Flat, Baldwin Pond from the 1940s. And then now you can see that that area has completely dried up. There are actually a few small holes of wetlands, but it can give us insight into things like climate change and how hydrology of the whole region is being affected. And then this upper right-hand corner is a flow path that flows every 3 to 6 years and connects this whole series of wetlands along our property. And so connectivity is an important concept in wetland conservation. And then starting to finish up here with the Jones Center part, we look a lot at hydrologic thresholds for things like wildlife. If you look at the figure there, that's the distribution of annual hydro period days, so the number of days of inundation each year. And the two red lines, dashed red lines on there, show the minimum breeding needs for these two species, gopher frog and what's the salamander called? It's right up there, striped newts, sorry. But if these species don't have at least those minimum inundation periods, they can't breed in these wetlands. And so they start to disappear from wetlands incrementally, one at a time, until hopefully all the wetlands don't dry up so that they can't breed for several years in a row. And then I'll finish up by just talking a little bit about some stuff we're doing now that Francis is going to lean into in a lot more detail, but we're very interested in landscape water storage. because landscape water storage controls the extremes in the environment. So if you have a lot of water on the landscape and you have a drought, those wetlands are slowly leaching water into the groundwater and buffering against drought. At the same time, if you have a very large rain event, those wetlands can absorb a lot of that water and keep it from getting into nearby creeks and rivers, keep the water quality higher, but also help prevent flooding. And when you have 11,000 wetlands on a landscape like this, even though many of them are small, that aggregate effect of all those wetlands can be very important. And so to lead into the next part, we're using NASA SWOT, and also what you see here is a high-resolution bathymetric map of one of our wetlands, and we're hoping over the next couple of years to start estimating landscape water storage. With that, I will hand it off to Francis.
Great, thank you, Stephen. And I just want to recognize that most of the work I'm going to be presenting today was done by Suranjana Chatterjee, who is a PhD student in my group at Auburn. I'm an associate professor in civil and environmental engineering, so I run a research group that's focused on eco-hydrology, which is understanding relationships between vegetation and the water cycle. And being in an engineering department, a lot of what we're focused on in my group right now is figuring out how to manage and protect and restore wetlands in order to do some things that normally would need hard infrastructure to do, like improve water quality and control flooding. So just some background on why these geographically isolated wetlands are a challenge with remote sensing. For one thing, they're small and ephemeral, and so they're both kind of hard to see from a signal that's coming from space, and then they also dry and fill rapidly after rainfall. So if you have a satellite that's only passing over a site every so often, if you capture the wetland when it has water in it, that's going to affect the quality of your data. Also, many of these have emergent vegetation cover. So you saw the picture Stephen showed on the first title slide of the talk. There were trees in that wetland, and so if you just look at an aerial image, it's hard to tell that it is a wetland and distinguish that from the surrounding forest. They also have irregular shapes and shallow depths, so even if you have a really good estimate of the area of inundation or the depth, it's hard to convert that to an amount of storage. They're also not included in hydrographic data sets, so things like databases of lakes and national wetland data sets, and so that can make them, and we'll talk later about why that's important, but that means we don't have if we don't know the landscape very well, we don't necessarily know where to look for wetlands. And then we also have kind of that intermittent conductivity and subsurface flow that make it challenging to fit a model to their hydrologic behavior. So if a lot of times with remote sensing data in hydrology, we're actually taking that signal and putting it into some kind of model to predict soil moisture or evapotranspiration. And we don't have good physical models for the hydrology of GIWs. And so some of the limitations of existing remote sensing products for this is that, obviously many of them are coarse resolution that will miss small GIWs, or have coarse temporal resolution, which means they may fill, or the wetlands may not be full when they're passing over. And then also some of the optical sensors, cloud cover creates additional noise. So if you further reduce your temporal resolution because you can't see through clouds. Also, obviously, a lot of these sensors cannot see through vegetation, and so that's a challenge. Some of the altimetric missions that address some of these issues have had, like Topex and Jason, have had very coarse footprints, and so they've really only been effective for large lakes and rivers. But NASA SWOT, this new data product that we're working with, is really a new opportunity for wetland monitoring. So just a little more information about SWOT. So they have been kind of releasing data since 2022, and it's a big advancement in global surface water modeling. So this is using Ka band, a radar interferometer, and it's measuring water surface elevation, okay? And that's across 120 kilometer swath. And this is allowing us to have maps of water surface elevation. And when they initially established this, in terms of inland water bodies, the main goal was to be able to provide water surface and elevation for lakes and rivers. And they had a target resolution of 50 to 100 meters for those inland water bodies. And so that captures some of our larger GIWs. It still doesn't quite get down to a lot of the smaller ones. But a lot of the initial results coming out of SWOT suggested that it actually can get much lower than that target resolution. And in terms of the vertical accuracy, there was a kind of key previous study done in the Florida Everglades that showed the vertical accuracy was as low as 6 or 7 centimeters for those kind of large, swampy Florida wetlands that have passed over. And so our goal here is, based on all of this previous information, we thought that this product could have the potential to allow for monitoring of small and remote wetlands that previously we couldn't detect. And so this project we got funding from NASA is to attempt to extend the SWOT product to be able to monitor GIWs beyond kind of its existing mission of monitoring lakes and rivers. So from the previous slides, you're already very well familiar with our study area, but we're working in the Doherty Plain, and this is a karst landscape, so it has limestone bedrock that is prone to erosion. That can lead to the formation of sinkholes on the landscape, and often GIWs form in those sinkholes because they're low depressional areas on the landscape, and so one kind of key aspect of that is, unlike wetlands that are along a river or along a lake, because GIWs are not connected to a navigable water body, they are not protected by the Clean Water Act. Okay, and so that motivates a lot of what we do, is that nothing related to CWA regulation or monitoring applies to our wetlands. Even though they're hydrologically isolated, they're very ecologically active, like you saw all the cute animals they support. We also have done some previous research showing that they store a lot of sediment, especially when they're surrounded by agricultural fields. There's also a good amount of emerging information suggesting they're highly active, especially in mitigating nitrogen pollution from agriculture. So they process a lot of the excess nitrate fertilizer coming off of ag fields when they're near agriculture. So our goal was to assess the SWOT pixel cloud data. And so this is a level 2 product that the main SWOT releases were level 3 vector products, which are providing for known lakes and rivers that are in those hydrographic databases. It provides water surface elevations for those as a GIS shapefile. We went down to the Pixel Cloud product, which is actually showing kind of point returns from the radar to see if we can get a water surface elevation from that. And then we're going to take the field data produced by the Jones Center and determine how well that matches up with our satellite water surface data. And identify any sources of discrepancy between that and figure out if it's not working, why is that the case? We have, as you saw, we have a lot of wetlands that we have data for, and we're hoping to eventually do this an analysis for all of the wetlands where we have the water level loggers recording 15-minute water level data. We selected 5 wetlands to start with as a kind of our first test set of wetlands, and the reason for this is that in all of these wetlands, a student who was working with us previously created high-resolution bathymetric maps of these. So if we know the depth of water in the wetland, we know what the surface inundation area should be from that map. And so that gives us a lot of prior information about kind of what should the satellite be seeing if it's looking at these wetlands. And we also, from that, when she designed that bathymetry study, was trying to do a variety of wetlands. And so we have wetlands that we're calling pond wetlands. These have an agricultural contributing area, and because of that agricultural runoff, the vegetation density in them is very low. So they're more if you see them when they're full, they look like small lakes or ponds. However, we do consider them wetlands because they have that strong annual wet up and dry down cycle. So unlike a lake that might hold water year round, these are dry for part of the year. We have a swamp, and so that is where we have trees as the emergent vegetation. And we kind of expect this is going to be the most challenging one to see with remote sensing data. And then we have 2 marsh wetlands that we're looking at. And so these are ones with herbaceous emergent vegetation. And so we have a range of sizes from pretty small, below a hectare in size, up to 10 or 12 hectares for when full for our larger wetlands. And so in each of these wetlands, we have one of those water level loggers at the deepest point in the wetland, recording water level every 15 minutes. And then, while we mostly trust our bathymetric maps just to kind of double check, when we know a SWOT pass is occurring, the Jones Center sends technicians out to a couple of our wetlands to walk around the edge of the wetland boundary with a GPS and get a very accurate map of, for that specific pass, where is there actually water. And then, as I mentioned, we have detailed bathymetric maps for each of these. And so here's some images of wetlands showing where the SWOT pixel cloud points have been generated. And so the blue line is showing the field measurement of the wetted area of the wetland. And then the red is our estimate of the maximum inundation boundary of the wetland. And so, you'll see we're returning some points in those wetter areas of the wetland. All right, and so just some, this is a paper that we have in review right now, but one thing that's helped accelerate our research is a master's student who worked with me and Stephen and graduated this winter, developed a new method for surveying wetland bathymetry using a commercial fish finder. And so this is now possible because they're putting much better GPSs in these commercial fish finders. So this thing only costs about $200. It can be towed on a fishing line by a researcher just walking back and forth across the wetland. And it provides actually really nice data that can be merged with a high resolution DEM to provide wetland bathymetry. And so whereas the other kind of established method for doing this would either be to do a very detailed survey with a GPS or to use a terrestrial LiDAR to scan the wetland when it's dry. She actually validated this against those terrestrial LiDAR scans to make sure this actually works right. But this has helped us to accelerate our wetlands research, is having these bathymetric maps. So here's an example of what this looks like. We take kind of the original LiDAR DEM, get the sonar measurement from the fish finder, and so when the LiDAR DEM, and this is from an airborne LiDAR, comes across, it catches the water surface when it's going across the wetland. We merge that with the sonar-based DEM, which is actually seeing the wetland bottom, to get a sonar-corrected DEM, which gives us a bathymetric map of the wetland. So this is just some more on kind of what these look like, how we ground truth it with a laser level. And on the left, that's what the cloud of sonar points looks like. So that's just someone walking around the wetland. And then it produces this nice image. And I think one takeaway from this is you'll notice it is a very irregular surface at the bottom of the wetland. That's in part because we have alligators burrowing in the wetlands. But also, if you think about something like the swampier vegetated wetlands, a forest floor is not even, and that neither is this. We have tip-up mounds, stumps, different things creating that irregular surface. And so, it's good to have this information because we're interested in scaling this up as we get more into remote sensing data. And so this will give us an idea of, if we're measuring this wetland water level with the satellite, this is how that translates to a volume. And then how do we think about estimating that for wetlands where we don't have this kind of data? And so this is a comparison of those bathymetry methods, and it's compared to the terrestrial LiDAR. So The blue lines here are the sonar corrected DEM, and then you're seeing the red lines showing the that LiDAR data that we're taking away from that. So those two are kind of the closest. And then we also compared these to a geometric relationship for wetland bathymetry, which is used in a lot of larger scale studies to estimate wetland volume. And so that is pretty off for these. And so if we're trying to go from a satellite-derived water depth to a volume, this is a potential big source of error. And so as we survey more of these wetlands, we'll be able to estimate, is that a random error? Is that introducing bias into our estimates? And so this has been this is setting us up really well to get into kind of the later objectives of the NASA project of going from remote sensing data to water storage estimates. All right, so getting some into the methodology for the NASA aspect of this. We extracted the level 2 pixel cloud product, and that is a lot of what John's group is doing up here, is actually pulling those giant data files and sending them to us in a nice format that we can open in GIS and work with. And so currently we have these for version C over the study area for 2024, which was a nice wet year. We've got some good points when our wetlands were full to analyze this. They just released the version D data, which is the next one, for that 2024 historical range. And so our next big step that we did not have time to do before we came up here and gave this talk is to rerun all these methods using the version D data and see if they look any better. We'll talk some more about this later, but just some of our initial probing of that data, it does seem like there's some pretty substantial improvements in it. So those pixel cloud netcdf files are converted to shape files we can work with sort of for this point level wetland analysis. Right now we're taking the data sets and clipping them to the maximum inundation boundary of each wetland, just to see kind of what is all the stuff that we're seeing around a wetland when we do that. I think our next step in this analysis is going to be actually clipping it to kind of a variable boundary based on the measured wetland water level depth to see if we get something different when we actually look inside the actual inundated area on a given date. And so we're pretty closely following with our methods right now the paper from the Florida Everglades that looked at using SWOT for wetland water surface elevation. And with this data, coming up with a good filtering algorithm is kind of the key to getting the result you want. And so the first thing that we did was for each pixel in this product, a land surface classification is provided. And most of the points within a wetland boundary are classified either as open water or as water near land. And the study in the Everglades filtered out anything that was not classified as open water. And so that was the first thing that we tried, is let's just only use the open water points. So that's filtering process 1 for us. We filter those out and then compute for everything that's in the wetland boundary and classified as open water. We take the mean water surface elevation for those and compare it to our measured wetland water level. We found when we did that, there were a lot of SWOT passes and measurement dates that we had no data points for. It took out everything, especially for the more vegetated wetlands. So then we said, well, we probably need to dig into these water near land points a little bit. And as we got into those more, and kind of looking at the elevations that they were providing, a lot of them were kind of outlierish elevations, so they looked a lot higher than they should be. And so that led us to kind of look into those a little more, and we realized that there is a geolocation quality flag, and that was a good way to separate out what was an outlier elevation to what actually seemed reliable. So what it seemed like was, if you had a point with a bad geolocation flag, it was probably hitting wet land or wet vegetation somewhere outside the wetland and reporting an anomalous elevation, whereas if you had good geolocation, that was in the wetland, actually catching wetland surface. And so our expanded filtering took water near land points only if the geolocation flag was 0, so perfect geolocation essentially. Okay, so first, looking at the medium pond wetland, and so this is the one that has a relatively open water surface, very little vegetation. This was one where we actually got a lot of open water classified pixels. And so the figure on the left shows only the open water pixels, and that actually did pretty well at getting the measured water surface elevation. We're still kind of working out how to figure out what the exact matchup is between measured and, what should the intercept be there. But, so we're mainly looking at the agreement of the slope with this, and we want that to be near 1, and we want the R squared as well to be near 1. And so we're doing pretty well with that. When we do the expanded filtering, our R squared goes down a little bit, but we maintain that slope relatively close to 1. And so this, as we were developing that expanded filtering, we were looking a lot at the results from this wetland to see if we add in those extra points, does it deteriorate the relationship there? And so that was kind of how we came on using that geolocation flag as being very dependent for whether or not it creates disagreement there. And so, this is for the medium pond. We also have that small pond wetland that was only 0.7 hectares, and we didn't get good returns for that. I think that one is just too small. If we go to some of the vegetated wetlands, so even with that expanded filtering, our medium marsh wetland only had 6 valid SWOT points during that year of data of the overpasses. But the R squared is still reasonable. The slope is a little higher than we would like it, and there's a lot of uncertainty there. So we're still filtering out a little bit more than we would like with the more vegetated wetlands. So like I said, the small pond did not have, it really only gave returns when it was very full. And so, that might be a matter of, with some of those smaller wetlands, we can just say, yes, it has water in it, no, it doesn't. And it may be more of a binary signal there. In terms of looking at the large swamp wetland, and so this is the one with trees in it, we did the filtering and it was filtering out a lot of the points. But one thing is that when we looked at all water near land points over the swamp wetland, and so this is the comparison for those, we get kind of a cluster of points that has a lower water surface elevation and then a cluster of points with a higher water surface elevation. And we find that the difference between the two is about the canopy height for that system. And so our hypothesis there is that we're getting some backscatter off of the vegetation, since anywhere between the top of the canopy and kind of the bottom of the canopy is probably that range where it's hitting some vegetation and bouncing around and giving a bad signal there. And so, obviously we got some good data and some not great data. I think one thing to keep in mind is we're only looking at 5 wetlands here, and one of them was really too small to be good anyway. If we look at, so what this is showing is the colored points there are when we had good data for each wetland. And the bar graph on the bottom shows the water level in just the medium pond as an example. And so you can see the clear hydro period there where the wetland is wetting up in kind of late spring and then declining. And so, when those blue bars are very low, there's really not much there to see anyway. And so when the wetland actually had water in them, we're getting at least one wetland with data for a lot of the time points. And if we expanded this to more wetlands, we might be able to fill that in a little more. And so, one of our goals with this was not really to be able to measure, and when we set up the objectives for the project, we weren't shooting to be able to measure every wetland on the landscape with SWOT. Our goal is to be able to catch a few wetlands and then get an idea of how much water is stored in these overall on the landscape. And, Stephen has a paper in review right now showing there's actually very good correlation between wetland water levels. So if we can measure a few wetlands, that gives us a good indication of what's going on across the landscape. We're also seeing that as we're poking around with the version D data a little bit, a lot of the quality flags are looking a lot better. They've improved. There were some problems with the geoid in the version C that it looks like they've been able to improve in the version D. So we're hopeful that some of those water near land points will have better geolocation and we'll get better data quality out of those. So kind of our next steps here are, obviously we're going to rerun all of this analysis with the version D data, see if it improves to the point where it might be giving us something useful. But as Suranjana and John were both at HEU last year, and we're noting that a lot of the people presenting on SWOT stuff, they were not just using SWOT, they were using SWOT in conjunction with other products. And so I think using some of the either optical or side angle radar data, there's good evidence that can be helpful with determining how much backscattering we're getting off of vegetation. And so we're going to be exploring that, as well as some additional potential filtering on cross-track distance. So maybe potentially identifying some points that might be bad based on where they are in the swath. And then finally, NISAR data is beginning to be released. And so this is another radar product that has a lot of promise for hydrology. And so we're interested in exploring that as well to see if maybe that is really what we should be using for geographically isolated wetlands. So again, this is kind of the key findings. Our Pixel Cloud product is great over open water. It's still kind of struggling with vegetation. Another common theme we've heard in working with SWOT is that there's really a trade-off between filtering and the amount of data you end up with. If you filter too much, you end up with no data. If you don't filter enough, you end up with bad results. And we're very much in that boat of kind of struggling with that. So that's kind of where we're at right now with the project. We're here in Huntsville for the rest of the day and tomorrow morning. So if you have any ideas you'd like to chat with us about, we've got time to meet with people this afternoon and tomorrow. And thank you all for coming. And I think we're at the end where, I think I talked about all this. So we want to acknowledge our funding sources and all the people who do the field work for this project, but we'd be happy to take any questions as well.
We have time for questions, anyone?
Sorry, I might have missed in the beginning. So what is the minimum size of the water body that it can detect?
Sorry, the minimum size of water body.
Yeah, or the wetland or that it can.
1.5 hectares?
Yeah, so about the smallest one we look at is 0.5 hectares, but they all dry down completely. So they all essentially have area of 0 at some point during the year. But the smallest ones are about half a hectare.
Okay. And the second question is there like a minimum depth to the water body that it can detect meaningfully, or is it?
So in terms of the minimum, the water level loggers, I think, when do those start going bad? What's the minimum depth?
Centimeters, maybe 6 if you wanted to be really safe.
So like a few centimeters, 5 or 6 centimeters. The fish finder we use to map bathymetry, that bottoms out at 15 centimeters. That's the minimum detectable. But I think when these wetlands have what we would call, holding water, we would say probably 10, 15 centimeters is where we start calling them dry.
Yeah, a lot of them are pretty bowl shaped. They have pretty steep sides and then a flatter bottom. So when it goes dry, it tends to go dry fairly fast. So there's not a lot of time when you're going to be in that range of 6 to 10 centimeters. So it's either wet or it's drying down rapidly.
Yeah, and a lot of them have various low points. So you might go from continuous coverage to there's water here and there's water here and there's water here. as they kind of dry down.
Yeah, some of the larger ones especially.
Yeah.
Hey, thanks for coming by. It's good to have you in Huntsville. The differentiating between like a pond and a pond wetland, is it
Mhm.
basically coverage, right? If it's full all year, it's pond. If it dries up, it's a pond wetland. Is there a classification of, I mean, just, growing up, and I'm not from this plains region, but up here, there's a lot of like isolated farm ponds.
Mhm.
Some of them are dammed up, but there are
Yeah.
some that are isolated, and I'm just wondering, is there a classification between pond and pond wetland?
So I don't think anyone has like an official legal classification. Like there have been actually very detailed legal classification of what is an ephemeral stream and what isn't. And we don't really have that as much for wetlands, I don't think.
Yeah, I mean, the temporal nature of the water, but also the maximum depth. If the maximum depth gets beyond about 1.5 meters, then it's hard for vegetation to root in the soil and then maintain, either a leaf that's above ground, or if you've got SAV, submerged aquatic vegetation, they start losing
Right.
sunlight. So, I mean, the one pond that we showed, Gator Lake, doesn't have a lot of emergent vegetation, so that's
Yeah.
right on the edge of being what we would consider a pond versus a wetland, but it's
Mhm.
not a clear.
We've seen it dry up completely.
We have seen that dry up.
And I think
Yeah.
it would have more emergent vegetation if it wasn't if it didn't have a peanut field dumping sediment
Yeah,
and
it's-
nutrients into
Sure,
it.
yeah. Or somebody just digging it out.
Yeah. Mhm.
I guess towards the end, you were talking about, basically looking with SWOT with other data sets, and, your work has been mostly focused on water level and capacity, but you mentioned before, like your carbon nitrogen, dynamics, or that's one of the kind of goals you're trying to get to.
Yeah.
And so, with the optical satellites, you do get less temporal coverage, but you still get some resolutions that are comparable, and I'm wondering between like some of the optical to look at nutrient dynamics, eutrophication, or some of the hyperspectral satellites that some folks here in the building have started using, PACE, I think. Just wondering, is that a component of thinking about it, like water level, but also the spectral and kind of nutrient level? Just, thoughts.
We haven't looked at it at that yet. A lot of the kind of sediment and nutrient and carbon work we've done has all been on the ground measurement. Since there's kind of, with these systems, there's still a ways to go with that. Just kind of understanding basically how they function. The one area where I have seen some of that work is actually trying to get at the suspended solid content of it with optical remote sensing. I've seen it done with drones, of trying to get, based on the color of the water, essentially how much sediment is suspended in it. You get into a lot of struggle with like the relationships are very localized. So the relationship you develop for this wetland between the spectral signal and the TSS content falls apart when you take it outside. And that's partially variation in soil, and soil color is highly variable across areas. But it's a challenge. That's the one area where I've kind of seen some examples of it, but I don't think that's necessarily on our radar. Probably should be.
Not the remote sensing aspect of it, but we've got multiple, or I'm at least a copy on multiple proposals right now, one with Francis, one with a colleague at Jones Center, to look at there's this big temporal aspect of nutrient transformations and storage, and it's way more complex than you would think it would need, than it needs to be, so we're trying to dive into some of those temporal variations and how
It's the
nitrogen,
wetting and
for instance.
drying dynamics that are a lot more complex here than in a lot of other systems, and that all, if you think about like the denitrification rates, they're a lot different if you've got, fully saturated soil versus partially saturated soil versus dry soil, and that's all fluctuating throughout the year with the hydro period.
within a
in the
year,
wetlands, yeah.
year to year. This year's a very dry year, so we're trying to get funding to look at the impacts of drought and fire. You know, seeing that wetland burn through a few weeks ago.
Mhm.
So what impact does that have on nitrogen transformations? Yeah, so there's a lot of mechanisms that we're trying to get after.
The-
Go
Go
ahead.
ahead.
No, finish.
No.
You're in the same topic.
I'm switching topics to
Yeah.
ET for a second, go ahead.
Oh, okay. So I think in the last, you did mention about using NISAR, and
Mhm.
I think major difficulty is with the vegetation, right?
Mhm.
So SMAP or NISAR, they had this vegetation water content product or vegetation optical depth, which sort of tells you the density of the vegetation. I think one of the factors in our analysis, which is, yeah. So maybe that could be one way to tease out that in the dry season, so if the vegetation density is really higher, that's the signal that dominates the L band or the P band, which you would be looking at.
Yeah, and
So-
I think Surnjan, did you look at some of that for your proposed, she's doing most of the NISAR exploration.
The L-band radar, it actually penetrates through vegetation, so we are more into like the NISAR data rather than SMAP. SMAP isn't L-band, right?
So that is L band, it doesn't have the radar component though, it only the radiometer component.
Okay, okay.
Yeah, and it's very coarse.
Okay,
I think
that's another issue that we, because our wetlands are so small, so we need at least like a good resolution to spot those difference.
Right.
For example, like there is Alos pulsar, right? Like, but that is also coarser. That is working really well for the big wetlands, but for ours it doesn't work.
Even if it is C-band, that's great, because that only looks at the vegetation part. Higher the frequency, more it looks at the vegetation rather than the soil. So, that would probably be good to tease out some of this vegetation
Mhm.
part
Yeah,
from, the impact.
I think
So that's
Sentinel-1 could be like another helpful thing. Sentinel-1.
Yeah, that could also be used. Yeah.
I have a project that we're.
No, you asked water quality stuff and then you
Okay.
should run off. I was like, damn it. You said it already.
Have you thought about, like, ET data sets? So their project with OpenET, which is pretty high res, they just released it in the east. So thinking about the drastic changes in water level and looking at a spatial resolution, I mean, part of it was, I was gonna ask about, like, just the vegetation signal, right? That's
Mhm.
something that's super wet when, but then that also will vary drastically too, depending on irrigation, especially all of these are in agricultural areas.
Mhm.
But have you looked at or thought about looking at something like that?
Yeah, so there's another student who we're co-advising who's pretty focused on, and again, she's working more at the individual wetland scale, but she actually has an ET sensor installed in one of the wetlands, and she has started doing some work with OpenET data to try to see how it compares to that sensor. And then, she is also interested in comparing kind of the upland to the wetland ET rate, and I think, that might be something where they're gonna have kind of different sensitivities, so it might help get some idea of like, what is the wetland actually doing at a given point in time in terms of, if it has water in it, it should have a higher ET rate than the surrounding uplands. And so, we've started working with that OpenET data to see if it works for our wetlands, because there's that, and then also the Jones Center has an upland eddy covariance tower measuring kind of what the ET would be from the surrounding forest. So we've kind of got two endpoints there, and the ET data from the wetlands still kind of limited. You just put the sensor
You got
in.
a year and
Yeah.
3 months from.
And
two
it's
different
one
wetlands.
wetland.
Yeah, it's one sensor.
Yeah.
It's kind of a proof of concept study for us.
Yeah.
We are at Neon Site, which is an NSF program, if you're not familiar with it. And so we've got that eddy flux tower and some of the remote sensing products from Neon. We've made a lot of use of the Neon's LiDAR data not so much of their hyperspectral data, but that is available.
Yeah, I guess it'd be more in identifying, locating so much and trying to understand, but, yeah. But I think this OpenET data sets are gonna be, still TBD in terms of just how much fidelity they have, but.
Yeah.
The resolution is attractive. To say the least.
Yeah, we've also got a pretty rich, ground level data set in terms of climate data. So we have 2 dedicated climate stations, but we measure rainfall and temperature just dozens of places across the landscape. So we can do things like, Piedmont-Monteith and compare. Yeah, that's been sort of the gold standard so far. We've always assumed that our ET in our wetlands is pretty much just limited by atmospheric demands. So basically, actual ET is 100% of PET, which, if that's true, I'm not sure. I think
Probably not right now.
Not right now,
Yeah.
no. Maybe for the
But
trees.
there really is the difference, right? So
Yeah.
it's your building ratio changes within, 20 meters from wetland line.
What we really needed for this year was to have a wetland like that, which is, those are all deciduous trees, so the canopy right now is open. We needed it to wet up while the canopy was open so
Yeah.
that we could test some of the concepts with SWOT, but again, we're just praying for rain.
Yeah. Is there, in the, the most simplest sense, how good does just precipitation data correlate with wetland? We have very good, precip coverage, and can you just?
We use, we've got pretty good results with using Palmer Drought Severity Index. I think that was the best. We've got a paper in review right now, looking at correlations of wetlands to each other across the landscape. And Palmer Drought Severity Index, I don't remember how much variability explained in wetland inundation, but because that's basically a water balance type equation over time.
But it seems like
Well.
we've also had better luck with water yield than with precipitation, because it does seem like you need to account for the evaporative demand
Yeah.
when you look at how is the wetland going to fill. It's pretty sensitive to that.
And then on this, do you happen to know if base flow sort of contributes to wetland water levels?
So some of them we think are groundwater connected, we're
Ah,
fairly sure.
Oh, that's interesting.
Yeah.
Yeah.
There's debate about that, rarely groundwater connected, but I do think from another student I had that did more hydrogeology work, that when groundwater drops, it increases the recession rate of the wetland. So the wetlands are losing water to ET. Some of them are also potentially connected to groundwater through the sinkhole, so they're not 100% watertight. So when groundwater drops, and groundwater at Jones Center can be anywhere from a meter below the surface down to about 15 or 16 meters. So it varies where you're on the landscape. But the recession rate can go, how fast the wetland drops gets a lot faster when groundwater drops. But there's not a lot of groundwater input into the wetland.
Yeah.
So it kind of underpins the soil moisture.
But most of them are functioning as a perched water table, essentially.
Yeah.
And don't you have a lot of farmers pulling
Oh, yeah.
out of the groundwater?
Yeah, they're
We've
not
seen-
pulling from the wetlands, but they're irrigating, but that's from a pretty deep wells, that's from the,
So we've seen,
aquifer.
we've seen our groundwater level drop from 1 meter to 10 meters in 2 weeks when all the farmers turn on their spigots in June, basically, because groundwater has a directional flow to it. It flows from northwest to southeast. A lot of our wetlands are kind of in that path, and so groundwater can drop out really fast when they turn those spigots on.
I just had a really simple question. You guys were talking about the, if 2 or 3 wetlands are wet, then it's gonna indicate the rest of them are wet. Is that the same for the, non-vegetative wetlands, the, open pondy ones versus the heavy canopy ones? Or is it different based on the type?
so it seems like there's some difference in recession rate based on the vegetation type, so some of them dry out a little faster than others, and so that we'd probably need to have some factor of what is the vegetation type and how does that factor in? And then I think the one thing we do need to look into that we haven't explored as much is how does the irrigation around the ag wetlands affect that? Because, you know, I imagine wetlands that are all in irrigated ag fields might correlate to each other, but it might kind of decouple them from the surrounding landscape a little bit. Which is scary because that's the one we're having a good luck measuring is the ag wetland.
Wasn't some of this wetland in southern or southeast Alabama? Or was it mostly in
Some of the
Georgia?
Darty Plain is in southeast Alabama.
Cause we know from UH, the irrigation line of Georgia and Alabama is very prominent for remote sensing. It's very much irrigated to not irrigated.
Yeah.
So I was just curious if there was any just difference, if there was a big enough like overlap in that southeast Alabama.
Yeah, we don't have any study sites in southeast Alabama. We're all right around where they're located in Georgia. But yeah, that would be, if we ever wanted to propose studying the difference between irrigated and not irrigated, or if we can get SWOT to work, we could do it without having boots on the ground. I will say, you know, one thing that is a challenge is getting into work on ag wetlands. We're lucky the Jones Center has good connections with some of the local farmers who let us work on their land. Because unless it's an ag research station, it's kind of tough to get in touch with people and get those connections made.
Yeah, we try not to make enemies in our local community. Just let that be a lesson. You know, we all care about wetlands and the environment, but we also try to work with our neighbors as well as we can.
And I will tell you, I went to the Jones Center last year, never heard of it. Just blew me away what they've got going on there. And the amount of research we can tie into is just incredible. And how many acres do you burn a year?
12 to 14,000,
A year, every year for the past
30 something years.
So it is really amazing. Lots of quail.
Lots of quail, yeah.
So thanks everyone for coming.
Thank you.
And if anyone wants to come talk to us, let us know.
Thank you. Appreciate it.